All right, so yet a third video with lemmas from section 2.1 and 2.2 that you need to be able to understand Theorem 8 in section 2.3, including lots of little proofs, the kind of things that you will see on tests, midterms, and finals in a linear algebra class. So, for example, this is a cute little lemma. It says if A is invertible, and A is row equivalent to a matrix B, then B also has to be invertible. So here's a proof. Okay, so A is row equivalent to B implies that there exist elementary matrices ES E2, E1, such that if you multiply A by those on the left-hand side, E1, E2, remember these are all elementary row operations that you're doing. After some number of them, you would get the matrix B, right? That's what that means. Well, note that all the EI are invertible by lemma. What lemma was that? Can you remember? Last video or so? Okay. And that A is invertible is given. So B here is a product of invertible matrices. Right? Because all the EI are invertible by this lemma that you're going to fill in the blank on there. And A is invertible, that's given. So B is a product of invertible matrices. What does that tell you about B? Well, that should tell you, therefore, that B is invertible. Why was that? Why should a product of invertible matrices also be invertible? That's by a lemma you just had. Which one was that? Can you remember? The sum of these two lemma numbers is equal to 3. That's a hint. Okay, so that's proved once you fill in the blanks. Alrighty, now lemma 6. Now lemma 6 actually has some parts of Theorem 8 in it from section 2.3. So we're definitely branching over into 2.3 now. Lemma 6 looks like this. Some parts, it's not doing things in exactly the same order that the book is doing their stuff in. Okay, so lemma 6 goes like this. It says let A be an n by n matrix. Such that 1, there exists another matrix C, also n by n, such that C times A is equal to the identity matrix. Okay, suppose that's true. Well, that is going to imply, too, that AX equal to 0, whenever we have a homogeneous system of equations like that, that's going to imply that x equal to 0 is the only solution. Okay, a little blast from the past here. This is going to imply, by previous definitions from way back, remember when you were looking at transformations in their kernels and their ranges? I hope you remember all your definitions back there. This is going to imply that the kernel of the transformation T sub A is just the smallest subspace. Remember, all kernels are subspaces, right? The one just containing the zero vector. Right? Let's remind you what T sub A is. Where T sub A here would be going from Rn to Rn. What is T sub A of X? Definition is, it means take the matrix A, this one, and multiply it by X. That's the definition of the map, the transformation. See, my lighting is kind of unfortunate. I sort of seem to have you in a glare. Not sure how I could change that. Maybe if I move this. That helps a little bit. Maybe. Okay. All right, so let me keep going here. Fourth part of this is that we will then be able to say T sub A is an injective transformation. What does it mean to be injective? Let me put that up here. We say T sub A is, any transformation, excuse me, not just T sub A, but any transformation is injective let's see, look at it, see if you can see this. Any transformation T going from vector space V to vector space W is injective, also called one-to-one, if and only if the following is true. Whenever T sub X is the same thing as T sub Y for two vectors X and Y that live in V. If that's true, if the mapping sends two vectors, give them the same image, then it's going to have to be, if it's an injective map, then that's going to force X and Y actually to have been the same vector in the first place. Okay, so we're going to be able to say that these three implications hold, and one more, we're going to be able to wrap this around this way and show that T sub A injective implies that AX equal to 0 is the only solution. Okay? I really do need to fix this glare, don't I? How can I get the glare to go away? Well, that might help for a little bit. Okay. Right. Okay, so proof. All right. So, 1 implies 2. I'll do that proof first. Okay. Why should that be the case? Suppose AX is equal to 0, right? So we start with that premise. But we do have some matrix C for which that's true, right? Well, if I multiply by C on both sides, okay, what do I get? This just becomes the 0 vector. Matrix multiplied by the 0 vector is always equal to the 0 vector. And CA is given as the identity. Well, the identity matrix multiplied by an n by 1 column matrix just gives you X, and so now X is equal to 0. So if we assume AX is equal to 0, we get that X equal to 0 is the only conclusion. Okay? So these things give me that we're done with that. So 1 implies 2, that one's done. implies 3. Can you guys see that? 2 implies 3 goes like this. So we're assuming 2. We're going to prove 3. Can you remember the definition of a kernel? Well, the kernel of a transformation is equal to the set of all x in Rn of this transformation, where t sub a here is going from Rn to Rn, right? Golly, I'm just walking you right into that glare time after time. Let's try that. Okay. So, if we're talking about the kernel of t sub a, where t sub a goes from Rn to Rn, then the kernel is the set of all things in the domain such that t sub a of x is equal to the 0 vector in W, which is here also Rn. Right? But that's the same thing as saying the set of all x in Rn such that, what does t sub a do? It just multiplies x on the left by a, such that ax is equal to 0. But we're assuming too that if ax is equal to 0, then x equal to 0 is the only result. So what is the set of all x's such that ax is equal to 0? Just the 0 vector. And we're done with that one. So 2 implies 3 is done. How about 3 implies 4? Where can I do that one? 3 implies 4. Not enough space for that over here. I'm going to put that one right over here. Actually, you know what? I'm going to get rid of this part. All right, so we did 1 implies 2, 2 implies 3. Now we're going to do 3 implies 4. Okay, that means if we assume this one, we get this one. Okay. Remember the definition again of something being injective. Transformation is injective. If whenever t of x equal to t of y, you get to conclude x equals y, right? So to show this transformation is injective, we start off with assuming t sub a of x is equal to t sub a of y. We'll have that this transformation is injective if I can end with saying, therefore, x is equal to y, right? So that would imply t sub a is injective by definition. How do I get there? Don't forget that we have, we can use some transpositions here. We could say this means t sub a of x minus t sub a of y is equal to the 0 vector. And don't forget that t sub a is a linear transformation. We proved that for spring break. So that means I have here t sub a of x minus y is equal to the 0 vector. But look what I'm assuming in 3. Right? Look at 3. The kernel of this transformation is equal to just the 0 vector. This statement right here implies that x minus y belongs to the kernel of that transformation, but belonging to the kernel which only equals the 0 vector. So that implies x minus y is equal to the 0 vector. And by adding y to both sides. That gives me x is equal to y, and therefore t sub a is injective. Done. And finally, 4 implies 2. So we do 1 to 2 to 3 to 4. Now we're going to go loop back around. And that makes, if you can show a sequence of implications loops back around, that will tell us that 2, 3, and 4 are interchangeable. Say that one more time, sorry. If you can show a chain of implications that loops back up on itself, then that means these 3 out of those 4 are interchangeable. One implies the other. Anyone, they're equivalent, we say. Okay, so I need to show 4 implies 2. And then we'll have a little closed loop here. 4. We assume t sub a is injective. And we're trying to show, therefore, ax equal to 0 has only x equal to 0 as a solution. So note, t sub a is a linear transformation. And thereby, it has to be the case that when it takes the 0 vector of the domain space, which is just Rn, it has to send that to the 0 vector of the range space, which is also Rn. Okay, so here we have this result, that t sub a looks like this. Well, that implies ax is equal to 0, right? Okay. Yeah, I don't need that line back up. So I have t sub a of 0 is equal to 0, but I also have that, so sorry, that's right. It does give me a times the 0 vector is equal to the 0 vector, but I also have, in part 2, I assume the beginning, the premise, I show that I get to the conclusion. So if also ax is equal to 0, my hypotheses of 2, t sub a injective implies since these two, so this looks like t sub a of 0 is equal to t sub a of x, right? T sub a of 0 and t sub a of x are both being mapped to 0. Well, t sub a injective gives us therefore that x has to be equal to the 0 vector. And that's what we wanted to prove. If ax is equal to 0, you have to get down to x equal to 0 is the only solution. That's 2. So we're done there. Okay. So you've seen how these 4 things have these 4 implications between them. And also you've been introduced to the idea, which theorem 8 relies on this bit of logic, that if a set of statements are in a closed loop of implication, then they're all equivalent to each other. Okay.